Hi everyone, Mrs. Basiaga here, and today we're doing spring force, spring energy, and solving spring conservation of energy problems. To start off, I want you to picture a spring at rest. This is called its rest length. If you stretch it past its rest length or compress it from its rest length, you now have two states where the object is changed in its position from its original. Whether it's compression or extension, we call this distance x, the change from the equilibrium length. In either of those states, a force would be applied. We call this force a spring force. And Hooke's law tells us that the more we stretch or compress a spring, the more force that spring applies. Hooke's law says that this is a direct relationship. As x, either the compression or extension, increases, the more force that's applied. We can see this because the line goes through the origin and increases at a steady rate. If it started to curve, we would call that section non-Hookean. It stops obeying Hooke's law. So, in Hooke's law, we have the force of the spring is related to its compression or extension, x. But there's a constant of proportionality in there, and that is k, the spring constant. Spring constant tells you how much force it takes to stretch the spring 1 meter of extension or 1 meter of compression. In fact, if you want to find spring constant, all you need to do is rearrange the Hooke's law equation. Instead of saying Fs is equal to Kx, what if you divide the x to the other side? The spring constant is force divided by meters of extension. So think of spring constant as the force needed to apply to stretch or compress your spring by 1 meter. On the graph from before, a spring that required a larger spring constant would require more force in order to stretch it. We'd see a higher slope indicating larger spring constant. This would be a stiffer spring, like the struts in your car. One with a lower slope would be a low spring constant, and that might be something like a slinky, something that it's really easy to stretch. Now, we need to understand spring constant in order to understand both spring force and spring energy. So let's see if we can tell those two concepts apart. On one hand, spring force depends on spring constant and x, the spring extension. Think of spring force as the amount of push or pull needed to return that spring to its equilibrium length. Because spring force is a force, that also means that it is a vector quantity. It has direction. Sometimes the spring pulls right, sometimes the spring pulls left. Spring force would also be measured in newtons because all forces are measured in newtons. Spring force could be drawn on a free body diagram. But spring energy or PES is 1/2 kx squared. These kind of look similar because they both depend on x and they depend on k. However, spring energy is the amount of energy stored due to position. Spring energy is a scalar quantity. It's measured in joules, and it would show up frequently in an energy bar chart. Notice that just like kinetic energy, spring energy can never be negative. As long as your spring is stretched at all, you always get a spring energy. And the fact that it's a scalar means if you stretch it at all, that energy could be released in any direction. Imagine stretching a bow and arrow. You could point it left or right or up or down, and it would still have that energy. That energy could be released and transformed to other types without having a negative effect on the amount of energy. The direction doesn't change the amount of energy because energy is a scalar. Let's say I have an energy conservation problem where I have a 2 kilogram mass compressing a spring. Let's say that we compress the spring by x equals 1 meter. And the spring is it's a pretty loose spring. Its spring constant is only 25 newtons per meter. And we want this ball, this 2 kilogram ball, to roll up the hill to an unknown height h. How we would use to solve a conservation of energy problem is the same as the steps we would use before. Start off with an energy bar chart. At point A, there's spring potential energy only. There's no kinetic because the ball is not moving. There's no gravitational potential because we're assuming the reference line is the ground. The objects in the system are the ball, the spring, and the earth. Now that ball rolls up the hill. But it rolls up the hill and it comes to a stop. So the kinetic energy is 0. When it's at point B, it's no longer touching the spring, so that energy is 0 too. Well, all that spring energy must have turned over to gravitational potential. So now we're going to set this equation. PES is 1/2 kx squared. That's equal to mgh. We're going to use this to find the missing height. On the left side of the equation, that's 1/2 times 25 times 1 squared. On the right side of the equation, the mass is 2. The gravitational field is 9.8. And then there's the height. So, doing some math in my head here, this means there's 12.5 joules of total mechanical energy. I did 1/2 times 25 times 1 squared. So there is 12.5 joules of spring potential energy. Now, because total mechanical energy is conserved in a closed system, there must be 12.5 joules of gravitational potential energy. So solving the right-hand side, this is 19.6 H is equal to 12.5 joules. Divide by 19.6 on both sides. So that's all, folks. Keep in mind, from this video, you should have learned that more spring extension leads to more force. You should have figured out that the Hookean section that obeys Hooke's law is a direct or linear relationship. The non-Hookean section is where your material gets irreversibly pulled apart to the point where it's damaged and no longer obeys Hooke's law. On this graph, you were able to get a spring constant K, and that's indicated by the slope of this graph. Spring constant is the second thing you should get from this video. By picking any data point in your graph and applying the spring constant equation, you could divide force by distance to get spring constant. A large spring constant is a stiff spring that is difficult to compress or stretch, and a low spring constant could be like a slinky that's really easy to move. From this video, you should be able to tell apart spring force, which is a vector and drawn in a free body diagram, and spring energy, which is a scalar and used for energy bar charts. They both serve a purpose and can be used to solve different types of problems. Finally, we did a sample of how to use the new spring potential energy equation to calculate a missing variable using energy conservation. All right, everyone, best of luck.